Our second changemaker of the evening is Yue FOONG from the Department of Mining and Materials Engineering as well. Yue is a second-year PhD student working under the supervision of Dr. Kirk Bevan. And he's going to talk to us tonight about how we can improve computer simulations of energy materials so that we can simulate how to build better batteries.
Thank you very much. How have our lives changed in the past few decades? Take a moment and look around us. It's not surprising to find that we have been relying heavily on electronic devices in our everyday life. Some of us rely on the wearable medical devices to keep track of our health so that the doctors can give a better treatment for us. And most of us rely on the portable electronics to work and also to connect with our dear friends and families. Not only we want to improve all these electronic devices to have a better quality of life, and there's another challenge that we are facing right now, is that we, as a great steward of this earth, would like all of these technologies to be green and sustainable for a better future. And that is why we see a trend in recent years that we would like to switch out the gasoline cars with electric vehicles. And also we would like to switch out the coal and gas power generators with solar farms and wind farms. And the question here is, why aren't they being applied widespread in our world right now? And the heart to this question is the energy storage devices that limits the potential of these technologies. And MARIANNA already talked about the solar farm and how battery can help in that regard. So my talk will focus on electric vehicles. So if we take electric vehicles, for example, we know that for the gasoline car, if we fill out the tank, it's really easy for us to drive 600 miles without having to refuel again. But when the first electric vehicle came out with General Motors EV1 in 1996, you can see that it used the lead-acid battery, and it can only bring us about 50 to 80 miles per charge. This is not enough. And therefore, 7 years later, we developed the second generation of the battery using nickel metal hydride, which doubles the mileage for our electric vehicles. But still, it's not quite enough for us to catch up with the gasoline cars. And therefore, we have been waiting for 15 years. And today, we can see that lithium-ion batteries have been revolutionizing our electric vehicle industry. By using lithium-ion batteries, we can actually drive up to, on average, 300 miles per charge. This is very impressive, but still it's not quite enough to catch up with the gasoline car. And the question here we want to answer is, what are the candidate materials that allows us to actually catch up with the gasoline car so that we can completely safely phase out the polluting energy resources? And not only that, another problem we have to face in electric vehicles is about the charging time. Even with the current technology of Tesla fast charging car, we need to wait about 15 to 30 minutes for a full charge of the car, as compared to 1 to 2 minutes in the gasoline vehicles, where we can just quickly fill out the tank. And this is the reason why a lot of people are worried to use electric vehicles to drive for a long-range trip. And this is why it's our quest to find a better material for our battery. And the problem is there's no way for us to know the performance of the material except for building the battery and test it out. And today, we are focusing on how to build a better batteries. And the very first step is to find the actual material. And this leads us to the periodic table. And most of us are familiar with it. As we can see for the periodic table, there are only 118 elements so far identified on the table. And from the first sight, we might think that, yeah, it might be easy for us to test each and every one of the elements out to find out the best materials. But materials, especially materials combinations, are numerous. Take lithium, for example. If we want to build a battery based on lithium, we have a lot of different combinations as we mix and match all the different elements together. The same case is true for the zinc air battery, which is another good candidate for green energy storage devices. Not only that, when we look at the different components of the battery, for example, the electrolytes, there are thousands and thousands of different combinations we can use. And these are only the tip of the iceberg. And finding the best materials combination for our battery is like finding a needle in the haystack without any map. And here we stand today. We try to come up with the battery material from all of these combinations, and researchers have to test them one by one. And from Marianna's talk, we know that doing research on battery testing is very tedious. And first, we have to come up with the proposal for the materials. And only after that, we can synthesize the raw material. But on this stage, we have to make sure that the raw material is stable enough and pure enough for us to test it. And only after that, we can use the raw material to build one component of the battery, for example, the electrode, to test its performance. And only after rigorous testing of the electrode, then we can build the actual battery and know its performance. As we can see in this simplified diagram, it takes months just to test material. And I bet most of the researchers sitting in the audience will agree with me about the struggles of doing experimental work. You have to overcome the trials and errors while trying the different concentration of materials. The case where there's downtime and breakdown of your equipment, you have to wait for it to be repaired. And also lining up just to use a very specified equipment to test the property of your materials. Using these long and tedious experimental procedures will not allow us to catch up to the ever-increasing energy demand, as Marianna has been telling us. How can we ever be able to design a better battery fast enough to allow for a sustainable future, as we are facing global warming right now, and we only have such a limited time to overcome it? And therefore, here in recent years, we have been trying to replace all of this experimental work with computer simulations. And theoretically, we would think that computer can calculate it very fast so that we can test the material's properties very rapidly. But in actual case, computer simulation is so intensive, such that even if we are using supercomputers, it takes as much time for us to simulate a material properties. And therefore, in Kurt's Bevan group, in our group, we try to find out the way for us to simplify and increase the efficiency of computer simulations, so that this allows us to do rapid material testing, and the researchers will be able to have a guideline of which material might be the best for their batteries and just focus on those materials in their research. And here, we learn two things. Is that computer simulations help us to accelerate the rapid material testing so that it helps researchers to come up with the best material. However, the second thing is computational method is very intensive and it takes a long time to perform. And this is why the talk we have today, we want to learn how to make computer simulation more efficient. Before we do that, we would first have to understand how computers simulate the energy storage devices. And in today's talk, I'll focus on supercapacitors, which is a hybrid between battery and capacitor characteristics. In a supercapacitor, we can see that it consists of a metal electrode submerging in an electrolyte solution. And in the electrolyte solution, there are charged ions floating around. As we are charging the supercapacitor, we are essentially stepping the potential to introduce electron into the system. And the presence of electron will cause electrostatic interaction with the ions. And this causes some movement in the system. And the movement of the ions in the electrolyte is the charging current that we detect in our supercapacitors. Continuous charging of the supercapacitor means that there is the continuous movement of the ions and translate into the charging current. And how the computer simulates this phenomena is by calculating and computing each and every movement of the ions frame by frame. And this will produce the data points to mimic the actual phenomena. This is very similar to how we are making movies by using different frames. Here is an example of a dancer, a 9-second clip that consists of 111 frames. Imagine if you were the artist and you were to produce this piece of art. You would spend 1 minute to draw each of the frame. And therefore, in total, you would spend at least 2 hours to produce the entire 9-second short film. This is the reason why our computational simulation is very intensive, is that we spend so much time computing each and every frame of our system, such that it takes such a long time to finish the entire simulation. And therefore, we have an idea. Wouldn't it be better if we can skip some frames strategically, but still be able to simulate the entire system? As we focus on this dancer analogy, we can see that the first 3 frames are so close together with each other, such that the actions did not differ much from each other. Therefore, we can safely say we might be able to skip every second and third frames. Instead of simulating a very small time step of 1 frame at a time, we would be able to skip and simulate 3 time steps at a time and eliminate the frame in between. This lessens our work, but still we are able to produce the dance very nicely and accurately. And thus, we can enjoy the same dance with only 1/3 of the work. But if we were to skip too much, we would see that this did not really capture the physics as well. It would be something very chaotic, and we can never enjoy it anymore. And here, we learn 2 lessons. First is that if we want a very accurate result, we use small time step. But the simulation and production time is very long. And if we use a very large time step, yes, we can increase the simulation to be faster and faster, but we lost a lot of details in between. And this is the same in our computer simulation as well. If we use a small time step, it is slow but accurate. But if we strategically skip some points in between, we will be able to replicate the result by using less work to do. But if we were to skip too much, this is where the analogy of the dancer breaks down. If you were to produce the dancing movie, the artist knows what frames come after one another, and he knows the future. But this is not the same with the computer simulation. The next frame of the computer depends on the data and calculation you have in the previous frame. So if you skip too much detail, you will get something very chaotic, and therefore we have a lot of noise in our simulation. And we can never replicate the actual physics of the system anymore. And so the question here is, how much of a time step is actually the optimal time step for us to capture the physics accurately using lesser work? And as we want to answer this question, we go back to the system that we simulate. In this system, when the computer calculates the physics frame by frame, we are actually tracking the movement of the ions in the electrolyte. And therefore, this gives us an idea that we can determine the time step based on the velocity increase in the ions movement when you introduce the electron. So conventionally, researchers try to come up with a very accurate result for their research. And therefore, they push the time step into a very low number. And this is the result that most of us might get. Here we see there are 2 regions in this graph. The region separated by the green triangle. On the left side of the triangle, we can see that the time step that we are using is slightly larger than the velocity. And therefore, we might be skipping too much that we miss some details in between. And therefore, there might be some inaccuracy at the beginning of the simulation. But at the second part of the simulation, we can see that the time step we use is very small compared to the velocity. So we are essentially tracking down every minute movement in the electrolyte that we are able to recover the stability of the system. But the small time step will result in a very slow simulation. So the next step for us is to how can we come up with a better and faster simulation? The very direct answer is to increase the time step, but this is not what we would expect for the result, because this is chaotic and noisy. As we can see, if we have a time step larger than the velocity, we have a fast simulation, but inaccurate. Here again, we learn two lessons. First, we want to maximize the time step so that we have a fast simulation. And second, we want to keep the time step below the velocity line so that we still capture the movement of the ions in the electrolyte enough so that we have an accurate simulation. So here in our research, we propose a third solution to this situation. So in our lab, we try to use automation to compute the time step so that it varies along with the velocity curve, just to keep it slightly below it. And this is the result that we got. If we keep the time step slightly below the velocity curve as it plateaus, we got a very fast simulation with the accuracy all throughout the whole spectrum of our test. So here we can see that if we want to simulate the energy storage of the supercapacitor, we have a method of using the traditional low constant time step, but this results in a slight error in the beginning, but very slow simulation of 30 hours per run. By using our improved method of varying time step, we can reduce the simulation time by 1/3 of what we used to have, but still maintain the accuracy. And the success of this research allows us to do a rapid material testing instead of having a very intensive and long simulation time. The optimized time step will reduce it by 1/3, but still keep the accuracy. Apart from the time step that I mentioned in this talk, in our group, we are also trying to figure out how to efficiently simulate and calculate the electron in the system, which further reduces the computational time. And also how we can efficiently calculate the math and matrix operations in our computer simulation, which further decreases the time to a very realistic realm where we are able to do rapid material testing to come up with a best candidate for our batteries. Not only that, by having an optimized computer simulations, we will be able to do parallel simulations, which further increases the capacity for our testing to screen off all the materials that we have been seeing so far and the materials that we haven't been exploring in the periodic tables. Here, we can see that computer simulation gives us the power to rapidly screen off the material so that we are able to catch up with the increasing energy demand. And at the same time, this allows us to have a better idea of which material is suitable for us to design a more sustainable energy storage devices. And therefore, a prosperous future that we all live in sustainable condition, where everybody have a chance to drive an electric vehicles, and every house powered by solar farms and wind farms will no longer be an empty dream, but it will be our reality. Thank you very much, and I would like to thank my supervisor, Professor Kurt Bevan, sitting at the back, and my research group member for their continuous support, and I would like to thank TISET for this opportunity. And thank you very much for being part of us tonight. Thank you.
So we have time for a couple of questions for Yue. Yes, please. And please use the microphone for the questions so that the video recording will hear
Thanks
it.
a lot. It's Michael Johnson from Siemens Canada. So You know, you inspired me tonight to think about how good is good enough. So,
Yes.
so how do you know, what are you looking for in when you're optimizing this way that you do the simulations, and how do you know you've gone to the right level?
Yeah, for our computation of the charging currents, we use an exponential fit for the decay of the current, and we set certain limits for the tolerance level. And from there, we can see how we can compute the actual optimized time set for that frame of the computation.
Any other questions?
Yes.
Avram Goldman from Pratt & Whitney, Canada. Thank you for this excellent talk.
Thank you.
The simulation method sounds like it might be applicable in other fields. Is there some way you could, say, brainstorm with your other counterparts and see if there's other fields that you're not familiar with where it might be applicable?
Yes. So in our group, we have simulations in various fields. I am focusing on supercapacitor, and my colleagues focus on fast field modeling, and some focuses on hydrogen fuel cells, and some even focus on DFT simulations. So we have the simulation for every single field that we might be able to tune our simulators to the specific applications. Thank you.
One last question,
Yes.
please.
Thank you for the talk. And I was wondering which kind of simulations you are doing, but you answered that one. You are doing a DFT. Then it seems that in your simulations, the time scale is important.
Yes.
But how do you translate that in DFT computation, and how do you manipulate the time scale to accelerate your simulation?
So for my talk today, the specific case that we apply this time step optimization is in the continuum model, which is far away from the DFT. So in the DFT, we have different issues that we have to tackle, for example, the correlation exchange terms. And these are the different computational challenges we have to overcome in order to optimize those systems.
Great, thank you. Well, let's thank Yue again.
Thank you.
Our final changemaker of the evening is Jennifer Martin del Campo from the Department of Chemical Engineering. And she's doing research under the supervisions of Professor Jan Kopuscinski in the Process Engineering Laboratory, Catalytic Process Engineering Laboratory, and Professor Sylvain Coulombe in the Plasma Processing Laboratory. And Jennifer's going to talk to us tonight about how you can harness the power of plasma to produce fuels from greenhouse gases. Jennifer.
One of the most important effects of global warming is the massive ice melting. And you will be wondering how a huge piece of ice that is melting is actually affecting us. I'm going to explain you why. Just like in the North Pole and in the South Pole, there's this huge glacier in the Hindu-Himalayan region. And this glacier is melting. With the current policies, scientists expect that 2/3 of this glacier
will be gone by 2100. However, even if there's a radical change in the environmental policies, and we keep this increase of increase of temperature in 1.5 degrees by 2030, 1/3 of this glacier will be gone. The problem is that this glacier is a water supplier of 8 countries. 2 of the biggest ones and the most populated ones in the world, including China and India. So this is affecting 2 billion people. And in this region, it's known for having a lot of agriculture. So there will be a point where there will be floods, but afterwards, they will suffer from water crisis. Also, this region has a lot of rivers that are providing electricity through hydrodams. So no water means also energy crisis. So we are not only having an environmental disaster, but we are also having energy crisis, political issues due to the migration that there will be from these countries to another ones, and also economical issues. Two of the responsible gases from this global warming are carbon dioxide and methane. And the level of them in the atmosphere have increased since Industrial Revolution. However, in 1950, there was an industrial boom in the plastic industry, aluminum industry, lead petrol industry, and concrete industry. The problem is that even small amounts of methane in the atmosphere are more hazardous because methane is 30 times more potent as greenhouse gas than carbon dioxide. But carbon dioxide stays more time in the atmosphere. And we all know about this natural cycle of carbon dioxide in the atmosphere. So we can give a look in the past and look over the last 400,000 years, where this level of carbon dioxide has been increasing and decreasing every 100,000 years. But in 1950, with this industrial boom, and also as a consequence of the Industrial Revolution, this level has never been higher. So it passed a level of 300 parts per million in the atmosphere. And now we are close to 400 parts per million. My colleagues today are making research looking for a carbon neutral future, to reach a plateau in this line, to keep it not growing up, but keep it flat. And all the efforts around the world are basically to reduce the greenhouse gas emissions. But this means reduce the emissions, doesn't mean reduce the current level of them in the atmosphere. Is there something else we can do? What about all the greenhouse gases that are already there? Or are we coming to a point of no return? Well, here's where my research comes in. To decrease this level, to not make it carbon neutral, but make it carbon negative. If we focus in recycling rather than in reduce, we can actually do something. And what if we take these greenhouse gases that are waste and we produce a valuable product out of it? Then this process is called upcycling. And the reaction that does this is called dry reforming. Dry reforming is a reaction between methane and carbon dioxide to produce syngas, a mix of carbon monoxide and hydrogen. And we have been told that actually carbon monoxide is pretty hazardous and toxic for our health. So why do we want to produce it? Well, when combined with hydrogen, this is like gold for the industry. And you might be surprised how many things here around you are made of this mix. Because syngas is used for power generation, also for fertilizers in the ammonia process, and chemicals in the Fischer-Tropsch process for the production of liquid hydrocarbons like methanol. It's also a substitute of natural gas, transportation fuels, consumer products, hydrogen for oil refining, and also direct reduced iron. This is a precursor of stainless steel, especially when we want to produce stainless steel with low content of carbon. And we can see this in the water pipes in your houses or in the body panels in your cars. So actually, syngas is pretty useful. But if this reaction is so great, why are we not doing it? Well, it's because this process is high energy intensive. It requires temperatures above 700 degrees. And not only that, it also requires a catalyst. The catalyst is a material that speeds up the chemical reaction, so we can get the syngas. But the problem is that having high energy processes is going to make us create more greenhouse gases. Basically, we are not solving any problem. We should find another way to create syngas, a valuable product that is pretty useful for our life. Well, luckily, there's another way. And this is called plasma. And before I tell you what I'm doing in the lab, I want to explain you what plasma is. In the next example, I want to show you in the upper part in the arrow, you have the state of the matter as you know it. And in the lower part of the arrow, you have how the atoms are behaving in the structure. So plasma is the fourth state of the matter. So imagine you have a cube of ice. Then we give some energy to it. We are going to melt the ice, and we're going to get water. So the molecules are going to move more free. Then we give more energy to it. We're coming to the gas phase. So the molecules are having more energy, and they are moving here and there. They are more free. But now let's see, we give way more energy to it. Way more energy than you can imagine. Temperatures close to the temperature of the sun. Then we will have plasma. We're going to start accelerate the electrons, and these electrons are going to hit the neutral molecules, are going to create ions and more electrons that are going to hit again the neutral molecules, creating ions and more molecules, more electrons. So at the end, we're going to have a pool of very active species consistent in ions, electrons, neutral molecules, among other species, and this is called plasma. But you might be a little bit confused because I'm telling you that plasma requires a lot of energy. But we want to avoid high energy processes. Well, luckily, there's another way to produce plasma, and this is with electricity. A good example of this is a lighting in the sky during a storm, or these plasma globes in the museum where you touch and all the rays are coming to you. Well, these are not hot, right? We're touching them. Now let me explain you how the plasma is acting in the dry reforming reaction. We have the reactants, carbon dioxide and methane, and then we're applying an electric field. So when I apply electric field, these electrons are gonna break down the molecules, are gonna rip off the molecules, and they are gonna ionize them, creating this pool of active species. But the molecules, they don't like to be charged. They like to be neutral. So the equilibrium, they are tending to equilibrium to recombine and produce syngas. In my project, I have developed a plasma reactor configuration called gliding arc, where carbon dioxide and methane are injected through the reactor where an electric field is applied, breaking the molecules. And if you see in the schematic these pink lines, this is where the plasma is happening. So we can see this pool of very active species happening there. So they are going to recombine, and they are going to produce syngas. If you're wondering how a plasma reactor looks like, well, this is my setup, the plasma reactor in the plasma processing laboratory. We have power supplies, 2 of them, and a reactor. And I want to show you a video of how the plasma looks inside of the reactor. So it's pretty cool, right? We are creating like lighting in a bottle. Now let's see how do we produce the syngas. I performed 2 experiments, one with low current, this means less energy, and one with high current. I'm gonna talk about first the one with low current. So when we have low current, we get some syngas, around 7%. But we also measure the temperature of the gas inside of the reactor. Note that I didn't apply any external heating. So basically, all the temperature that you can see here is coming for the movements of the molecules, for the reaction itself. So as you can see, we have this pretty steep slope increasing temperature during the first minutes of the reaction. Then, at around minute 30, it reaches a plateau, the steady state. So then we perform the other experiment. We are giving more energy to our process. So we were expecting more conversion, and we get more conversion. We have more syngas. But giving more energy will also imply, logically, to have more temperature. But surprisingly, we didn't find it. We have a smoother slope, and it reaches a steady state around minute 100. So the increase of temperature is not as high as in the other curve. Basically, all the energy we're giving to the process is being transformed into chemical energy rather than into thermal energy, meaning that we are producing more syngas instead of warming up the gas, which is pretty good news because basically we're making more efficient the process. If we compare our best result with the conventional method of producing syngas, we see a gap of 55%, but we also see a gap of 600 degrees Celsius in temperature. The question here is, how can we decrease this gap of 55% without decreasing the other gap of 600 degrees Celsius? Meaning, how can we produce more syngas without giving more energy to the process? And this is where the second part of my project comes in. To optimize the reaction conditions and to combine also technologies to help the reaction, like plasma catalysis. As I mentioned before, the catalyst is this material that speeds up the chemical reaction. And there's this known synergistic effect between plasma and catalysis, where the catalyst is affecting the behavior of the plasma, and the plasma is enhancing the behavior of the catalyst. So with this, we can say that plasma technologies are pretty useful to upcycle greenhouse gases, not only decreasing the current level of them in the atmosphere, but also producing valuable products like syngas out of them. By reducing these effects, by reducing this level of greenhouse gases in the atmosphere, we will be able to reduce the effect of global warming, meaning we will be able to reduce the melting of the glacier and avoid some future environmental, political, and economical issues. Thank you very much.
Thank you, Jennifer. Questions for Jennifer? Yes, please.
Hi, Jennifer. Max Scully, mechanical engineering alumni. So a little question about how the energy could be extracted from the syngas. So when theoretically comparing the energy input to creating it versus what would be output, what would be the overall efficiency of the process?
Well, currently I'm working on that. I have measured the energy that I'm putting in my process, and with the high energy process, high current, I have like around 120 watts, which is not so bad. The output, I haven't measured it, but that's where I'm working currently now on it.
Other questions?
Just a question. It's I guess what I think about it is kind of like you want to vacuum the atmosphere in a sense, right? So
Well,
is that kind of what the end goal is? Really, I mean, to reduce significantly, let's say, the carbon
if
content.
possible, it could be like, yeah, now like we're in the laboratory step, but the ones that we can optimize this reactor, the beauty of that is that we can pass everything through the plasma and create these valuable products, so yeah.
Hi, Jennifer. Maurice Melcaf, alumni from MBA. I wonder if you've done any comparison with carbon capture cost, and if this is much more promising from that point of view.
So far, I haven't done any comparison, but well, one of the advantages of my process is that basically we are just not capturing the CO2 and the methane, right? So we are also producing syngas, which is, as we saw it, it's pretty valuable for the industry. So this is one of the advantages. I haven't made the comparison, but it's a plan that I have for the future.
Thank you.
Thanks.
as a real non-specialist. You've got your source gases in your laboratory, and I'm wondering, I'm thinking, is carbon dioxide and methane there in the high atmosphere? If this works out really well, how do we get that to a plant on the ground?
Well, that will be like, that will be another PhD, I think. Yeah, I mean.
Yeah, surely the best way is to stick a plasma plant on one of those places that generates a lot of, that you're not going to hoover the atmosphere. That's ridiculous.
Yeah. That's a good answer, yeah.
Any other questions for Jim? Let's stick her again. So our first changemaker this evening is MARIANNA UCEDA. MARIANNA is a fourth-year PhD student in the Department of Mining and Materials Engineering under the supervision of Professor George Demopoulos in the Hydromet Lab. And MARIANNA is going to talk to us about how to build a greener battery. MARIANNA.
Energy is an invaluable resource. Access to energy has become fundamental for the promotion of human well-being and economic development. This is because we use energy in everything, from building our homes to powering our homes. Now, our current technology allows us to produce energy from a wide variety of sources, these being coal or gas, and this gives us a very large supply. However, this supply has an ever-growing demand placed on it. By who? Us. As of 2017, the Earth's population has reached 7.6 billion people. It's doubled in 50 years. And alongside this growth, so has the demand for energy. So in the course of providing energy for this ever-growing population, we have to consider its environmental impact. And by that I mean its effect on the surrounding land, on people and wildlife population, and on the amount of pollution that it might emit. The most common types of energy sources are coal and gas. Now, these have a very high environmental impact. And this is because they produce large emissions that impacts the surrounding air and water bodies. Additionally, the mining for coal and drilling for gas heavily impacts the surrounding landscape. On the other end of the spectrum, we have wind power. It has a lower environmental impact because it produces significantly less pollutants. The problem with wind is that it poses a threat to some bird and bat species. The same thing can be said about solar power. It has a lower environmental impact, but some types of solar cells use some toxic heavy metals during the production stage. Now, another thing we have to consider in this graph is the degree of control that we have over power production and power delivery. You see, we can make energy from gas and coal plants during any time of the day and during most weather conditions, but we can't make solar power if there's no sun. And we can't make wind power if there's no wind. So we can say that we have a high degree of control over power production and power delivery of coal and gas plants. Now imagine that we wanted to be completely green and switch to only using solar cells as our power source. What will we do at night? You see, the electricity that is powering this presentation was generated moments ago and delivered just in time. The grid is the world's largest supply chain with zero inventory. If we want to switch to just using green energy like solar cells, we need to be able to meet the energy demand during all times of the day for our society to be sustained, or we can't even begin to think about getting rid of coal and gas. Right now, if we use just solar cells as our power source, our supply and demand balance looks like this. The demand is met during the day when we have sun, but it is severely lacking at night. Here, what we need is storage. And we can do this. We can use lithium-ion batteries. And they're already being used to store energy during high production times, like during the day, for use during low production times, like at night. Effectively, it's become the storage. It's restoring balance between the demand and supply and making the use of just solar cells viable. So if we go back to our control and environmental impact graph, and we take that solar cell and we couple it with a battery, we can improve the degree of control that we have over at least power delivery. And the same thing can be done with wind power. Now, lithium-ion batteries are also being used to power electric vehicles, as opposed to the conventional gas engines, which also produce a lot of pollutants. However, they're not just used to power cars or buildings. We're already using them in our phones. This shows that lithium-ion battery technology has wide versatility. Why? Because there's many different types, and these types are categorized based on the type of lithium-ion material that it is using. For example, this Nissan Leaf electric vehicle uses lithium manganese oxide, whereas the Samsung battery uses lithium nickel cobalt manganese oxide. So not only are lithium-ion batteries at the forefront of environmental efforts, they're already incorporated into our daily lives. So let me throw a curveball at you. What would you think if I told you that lithium-ion batteries aren't completely green? If lithium-ion batteries are going to be part of the clean energy solution, we need to be able to say that they are green from start to finish, from production to disposal. Otherwise, they're hypocritical. Now, to understand how lithium-ion batteries might not be green, let's first look at how lithium-ion batteries work. A typical lithium-ion battery cell is composed of two electrodes, the anode and the cathode. These two are separated by a porous membrane separator and submerged inside of a liquid that we call the electrolyte. This is completely sealed, and the two electrodes are connected by an outside circuit. And this circuit is then in turn connected to the load. Now, with lithium-ion batteries, the electrodes are composed of coatings on top of a metal surface. And this coating composition will vary depending on whether it's an anode or a cathode. Anodes are usually composed of carbon, and the cathode is usually the lithium-ion material. Now let's look at these coatings on a molecular level. The anode is composed of carbon atoms arranged in a honeycomb structure, and we have layers of it. The cathode is composed of lithium-ion layers and a matrix, and this matrix composition will vary depending on whether the type of material that we're using. Now, the lithium ions can be completely removed or reinserted depending on whether the battery is being charged or discharged. As it sits right now, the battery is charged, and that's why we find lithium ions in the anode. If we were to connect this circuit, we would cause a chemical reaction. This releases the lithium ions, and this in turn releases electrons. The electrons flow through the outer circuit and become electricity. The lithium ions flow through the porous membrane separator and towards the cathode, where they can become reinserted. If we then take the system and connect it to a power source, we can reverse the reaction and return the lithium ions so they can once again be stored in the anode. Effectively, we've recharged the battery for use again. Now, remember how I said that the electrodes are composed of coatings? Let's look at how we make a lithium-ion electrode coating. The first material we put in there is the lithium-ion material. Now, these materials tend to have really poor conductivity. So we can improve this by adding conductive material. And this is typically done by adding a small amount of carbon. We also add a binder to hold everything together. These powders are mixed with a liquid called NMP. This gives us a slurry, just like paint. And just like paint, we can then paint it onto a metal surface. This is the conventional fabrication technique for lithium-ion electrodes that we use in industry. However, the problem with this fabrication technique is twofold. The first is that NMP is toxic to human workers. Also, it is explosive. So companies have to take into consideration the type of equipment that they're going to use because they're scared that it's going to spark and start a fire. And I'm pretty sure everyone will agree alongside Samsung that we don't need any more fires associated with lithium-ion batteries. So you're probably sitting there wondering, well, then why do you use NMP? Well, that's because of the binder. The binder is highly specialized because it doesn't degrade during battery use. It's also very picky. It only wants to dissolve in NMP. And we need it to be able to dissolve in NMP so we can make a uniform coating among these three components. That actually brings us to the second reason why this conventional technique isn't very appropriate. You see, with battery materials, we use very small materials. They're nano-sized. And what happens when you put this in a slurry is that it becomes extremely viscous, and it doesn't want to flow right. This prevents it from being able to mix properly and create and makes non-homogeneous or non-uniform coatings. So this is where my research comes in. We are using a different technique to make our electrodes. We're effectively using a different brush to make the coatings. And this brush is called electrophoretic deposition, EPD. Now, EPD is a simple electrocoating technique that consists of submerging two metal surfaces inside of a liquid. And these surfaces are then connected to each other by an outside circuit. Now, within this liquid, we place the lithium-ion material, the conductive material, and in some cases, a binder. And we mix vigorously to make sure that we have a very well-mixed solution. Now, we actually call it a suspension at this point because there are powders in suspension. And in suspension, these powders develop a charge. And whether they're negative or positive depends on the material itself, and it also depends on the liquid that we're using. If we then take the metal surfaces and connect it to a power source, it forces a charge to also develop on these surfaces. As a consequence, the powders will migrate towards the oppositely charged surface and deposit. This gives us the painted layer that we then use as an electrode. Now, the key thing that we have to keep in mind when we're using EPD is we need a stable suspension. And by that, I mean that the particles will not agglomerate or stick together and sediment to the bottom. If we can meet this expectation, then the liquid can be anything from water to ethanol. And that brings us to the key advantage of EPD. It has the potential to be environmentally friendly. Now, within the McGill Hydromet group, we use this submersion setup hooked up to a power source to make our electrodes. This is a bit dirty, so let's look at a schematic I drew. And the submersion setup consists of an adjustable height bar that holds the two metal surfaces in place and connects it to a power source. So the way we make our coatings is we submerge the metal surfaces. And once it is submerged, we apply a voltage. And this is very brief. It's only done from anywhere between 5 to 15 seconds. This forces a coating to form. We can then remove the coating and allow it to dry and repeat this for as many times as necessary to create a thick enough coating. And this is what our coatings end up looking like. The black or gray part there is the aluminum foil that we submerged, and on top of it is the EPD coating that we just made. So I want to show you how these EPD coatings compare to the conventional coating technique. But to do that, we conducted some tests. And for the tests that I'm going to show, the EPD solution that we used was a mixture of water and acetonitrile. And the particles that we suspended that ultimately became the coating was lithium titanate, which was the lithium-ion material, carbon, which was the conductive material, and a water-soluble binder. So before we can test these out, we actually have to make a battery. So we take the coating and we remove a 1 centimeter disc and we assemble it into what we call a Swage-Lock type cell. Now, this doesn't look like your regular AA battery, but it's what we use in the lab. And we can repeat this process for a conventionally made electrode. So we have a battery that has a conventional electrode, and we have a battery that has an EPD electrode. So now we can compare its performance. We can do that by charging, discharging, just like you would with your phones. If we do that, we can measure the battery capacity, and that is the amount of charge that is stored within 1 gram of the material. This value varies depending on the type of material that you're using. But for lithium titanate, that is what we used, the theoretical capacity is 175 milliamp hour per gram. Now, this is actually quite low, but we have an advantage with lithium titanate, and it's that we can deliver that power, that capacity very fast. We can also charge it really fast, and you want to be able to charge your phones fast, but you want to be able to deliver power fast when you're using something like a power tool that needs fast power delivery. So now, we're going to take this battery and charge for 5 hours and discharge for another 5 hours. So one cycle of charge and discharge takes a total of 10 hours. And for the EPD electrode, what we find is that we reach the 175. And there's a gradual decrease. This is expected in a lab setting. When we look at the conventional, we find that it's much lower. It doesn't reach the 175, but it's at an equal degree of degradation. So let's make it faster. Let's take 1 hour to charge and 1 hour to discharge. We see no difference. So let's speed it up even more. 30 minutes, 6 minutes, 3 minutes. Now we're really seeing a difference between the EPD and the conventional electrode. At 3 minutes, the conventional electrode capacity doesn't reach half of what the EPD does. So we can say that the EPD electrode performs better in fast rates. That's great. But now we need to know why. And the difference between these two was the way that we made the electrodes. So we took these electrodes, or the coatings, we cut them in half, and we imaged the cross-section. So up here, I have an image of a scanning electron microscope image of the cross-section of the conventional coating along the thickness. And the first thing you might notice is this chunk in the middle. What is it? You see, we have 3 different types of materials, right? We have the lithium titanate, we have a carbon, and we have a binder. So how can we know what this is? With the scanning electron microscope, we can use a technique called electron dispersion spectroscopy, where we can map out elements. Lithium titanate is the only material that has titanium in it. So if we then make a titanium map, we can see where the lithium titanate is spread out. And that's just what we did. So we found out that this gray agglomeration or chunk in the middle is lithium titanate, with the carbon and the binder spread around. Now, if we compare what this looks like with the EPD electrode and its corresponding titanium map, we see a huge difference, right? With EPD, we can say we have a more uniform coating. Now, if you remember what I said earlier, the conventional fabrication technique doesn't make very uniform electrodes, and now we can visually see that. So we can say, so far, that EPD produces very uniform electrodes that perform really well at fast rate. But what is the connection between the uniformity and the rate performance? Well, we measured the conductivity of both of these electrodes, and we found that the EPD electrode was 15 times more conductive. So let's look at a schematic of these coatings. Here we have the lithium titanate in gray with the carbon in black. Remember how I said that the carbon acts as it improves the conductivity of the overall material? It sort of acts as like a highway for the lithium ions and the electrons to flow through. For this material to perform, the lithium ions and the electrons have to reach the surface of the lithium titanate to react. And when lithium titanate is in contact with carbon, this happens very fast. But what about this middle lithium titanate? Effectively, this is like having a landlocked house that has no access to road. The lithium ion and the electrons can still reach it, but it's a lot slower when it has to flow through the lithium ions. So we don't have this problem with EPD because we have well-dispersed carbon roads and no landlocked lithium titanate. So now we can say 3 things. EPD produces uniform electrodes. This improves the conductivity of the overall electrode, and this ends with a better performance as a battery. Now, if you remember earlier, we were talking about combining lithium-ion batteries with solar cells. If we do this, then conductivity is a big deal, because low conductivity means high resistance. And when you have high resistance, you're losing energy as heat. And this means a low overall efficiency between your solar and your battery couple. But we don't have this problem with EPD electrodes. We have higher conductivity, so comparatively less energy is lost as heat. This means that our overall couple has a higher efficiency. So not only are we making lithium-ion batteries that perform great, they're greener, and now they have better efficiency. But you're probably thinking, well, you made those in a beaker, in a small glass jar. Can this really translate into industry? And yes, it can. I know this because it's already been done. The EPD has been scaled up. It's currently being used as e-ink or e-technology. And this is used to coat corrosion protective layers on top of car bodies. And this looks like this. We have a big tank, which is effectively my big beaker. And inside we have the coat or the paint that we want to paint on top of the car bodies. The car bodies are submerged. They're held by a rack and submerged inside of the tank. And a voltage is applied. And this forces a protective layer to form on top of it. And the advantage that this coating technique might have over the conventional direct spraying is that the rack itself that is holding the car body, if that's insulated, then nothing is going to deposit on it. So we have no overspray problem. We have no loss of material. And this same advantage can be translated to making lithium-ion electrodes. So in conclusion, I can say that electrophoretic deposition is a potentially environmentally safe electrode coating technique. Additionally, it makes electrodes that have excellent battery performance. And we know that this can be scaled up because it's already been done. So we can meet the energy demand and be green from start to finish. Thank you very much. Oh, yeah, that's I forgot.
Thank you, Marianna. If we have time for one or two questions. Jan?
Obvious question, do we have enough lithium in the world to actually do this nice thing?
That's difficult to say. To be honest, my specialty isn't knowing how much lithium we might have at our disposal, but right now, actually, I'm not sure.
That might be a big point, right?
Well, we do have a that's my advisor.
Well, in response to Jan, actually we have, and also we can just replace it with other elements like sodium, for example.
Oh, that's very true. Yes.
I have another question if you have time.
Yes, sure. Maybe use the microphone, please.
I guess I'm well enough, so
That's for the video, yeah, please, yeah.
So, I forgot my question actually.
That's okay. You can ask me afterwards if you'd like.
Oh yeah, you talked about the scalability, but how about the flexibility of your system? You know, you are working on titanate metrics, but how about other metrics like, let's say, iron phosphate metrics?
Well, that's a really good question, thank you. And yes, it's quite flexible. It all depends, like I said, if we can make a stable suspension. And in most cases we can. I've worked with a variety of different materials, lithium iron silicates, lithium cobalt phosphates, and I found that yes, I've been able to make a good coating. I've never actually tested it further as a battery, but depending on, if you can just make a stable suspension, you can use EPD.
Okay, maybe one more question.
I wonder if you could draw an analogy to supercapacitors and what's used to create them, which are now being used as a supplementary source of instant power, even in cars.
I'm not sure I know enough about supercapacitors to be able to make an analogy. So sorry.
Maybe one last question then, sure. Well,
ultracapacitors power density is about 1/200th of lithium ion right now, the commercial, just to answer that question. You referenced charge rates for the reference cell or the traditional cell, a decay of, it looked on your graph, something like half of the capacity by 30 cycles. Commercial lithium ion, typically for cars, is 80% over 1,000 charge cycles at 1 seat. Have you extended that test over time, over thousands of cycles, and seen what it looks like?
We haven't extended past 1,000 cycles. I've only made it up to 150. When I took 1 hour to charge and 1 hour to discharge, it went well into the 150 cycles with only less than 9% capacity loss.
Great. Okay. Well, thank you, Marianna.
Thank you.
Take our speaker.